Hello everyone, welcome back to Altium Academy. I'm your host, Zach Peterson. Today we're going to be talking about a topic that has come up in the Altium subreddit, and that topic is routing into SFP connectors. Now we've talked about SFP connectors in other videos. We've talked about them from the circuit design perspective when we were doing our Ethernet switch design video series, and we talked about them in terms of placement on a PCB as well as placement within the mechanical cage where the optical transceiver slides in and connects into that SFP connector. Today we're going to be looking at a question from Reddit that deals specifically with routing into those SFP connectors. Let's go ahead and get started. Now in this video, we're talking about differential pair routing into SFP or SFP plus connectors, or any of the other variant type SFP connectors. So there are QSFP, there are SFP28, there are different types of SFP connectors, but what we're going to talk about today really applies to all of those different types of connectors. The only difference is the data rate that you're working with, and of course the resulting channel bandwidth that you need to supply in your design. Let's go ahead and take a look at a question about this topic, which came through the Altium subreddit. This question, titled "Looking for Real-World SFP Plus Routing Tips," comes from OneResident1447. One resident writes, "Hey everyone, I'm currently working on a high-speed design involving SFP/SFP Plus interfaces at 10G, and I've already gone through most of the standard routing guidelines, vendor docs, app notes, etc. While those cover the fundamentals pretty well, such as impedance control, differential pair matching, via usage, I feel like they don't really get into the practical, minute tips and tricks that actually make a difference in real designs. For example, one thing I've been unsure about is when doing length matching, most guides say match within the pair and keep interpair skew low, but they don't really talk about how aggressive serpentine should be placed or how to avoid creating impedance discontinuities when doing tight meanders." Now this is a really great question, and it is something that we haven't really addressed on the channel. We've addressed little bits and pieces here and there, but we've never really address this in the context of SFP or SFP plus routing. Now we have talked about SFP connector placement. We've talked about placement of the mechanical cage that goes around the connector so you can slide in an optical fiber transceiver. And we've talked about circuit design a little bit for those SFP connector interfaces. So what we're going to do now is we're going to take a look at a couple of examples inside of Altium Designer. One of them is for a 1G interface, and then another one is for a 10G interface. As we're going to see here, they both use SFP connectors. They're actually very similar at these data rates, and some of the tips and tricks that we're going to discuss here really apply to pretty much any data rate and are just viewed as a best practice. So let's go ahead and jump in and take a look. Now the first project that we'll look at is an FPGA board which has two 10G interfaces, which you can see right here. Now I've shown some variations of this design in other videos, but we're going to look at this much more compact version here in this video. So here you can see the design in 3D with our two SFP cages. Now here, if I go into 2D, you can see here we have two SFP connectors, and then here on the highlight you can see where those lines are being routed all the way over here to the FPGA. So the routes are pretty short in this design. The other project that we'll look at is here in 3D, and it is the Ethernet switch project. And if you want to learn more about this project, take a look at the video links in the description. So in this design here on the top layer, we have our SFP connector. Here we have our SFP cage. And then here you can see we have the differential pairs coming out, going through some vias, and then going into the bottom layer and then routing over here to the controller chip, and the controller chip is located on the top layer, as you can see right here. Now, in order to successfully route over to an SFP connector using differential pairs, we have to take account of a few things in the design. First is, of course, the pair design. And when we design differential pairs, we're basically just selecting a width and a spacing that allows us to route into the connector and route into the pins on the network processor in the design. The next thing we need to focus on was actually mentioned in the question on Reddit, and that is the length tuning or meandering that's used in the differential pair. Now, that will impact something called mode conversion, and we've actually talked about mode conversion in another video on the channel. So again, take a look at the link in the video description if you want to learn more about mode conversion in differential pairs. Now, mode conversion is very important when you get into high bandwidth channels, especially something like a 10G interface. It also has limits in, for example, the differential pairs that are used in PCIe, and you can find other examples in different high-speed interface specifications. Now, one of the corollaries to these 2 points is the stack-up design, and in particular, the layer thickness that you use in the stack-up. The DK value is a little bit less important unless you have really long routes, because, of course, if you have a very long route, you could have a lot of insertion loss. Or if you have very high channel bandwidth, you could then have very high loss at high frequencies. But typically the layer thickness is much more important when you're working with like a 1G interface or a 10G interface. Now, another point that we need to talk about, which sometimes comes up at these data rates, is the via design and whether or not you need to use stitching vias, what the impedance of the vias is, those types of issues. Now, I can tell you that on a 1G interface, you can kind of do whatever you want with the vias because the channel bandwidth is so low and the deviation from the target impedance happens at such a high frequency that you're basically never going to notice any deviation in the via impedance from the target channel impedance. However, at a 10G interface or at an even faster interface like 25G or 56G, you are definitely going to notice when the vias are not designed properly. So that one requires a little bit of context, and unfortunately, a lot of the app notes, vendor guidelines, and data sheets don't really do a good job of providing that context. Now, another point related to vias is the presence of stubs, and there is sometimes guidance in a lot of very simple or non-expert high-speed design guidelines that says that every single stub is bad no matter how long it is, and you should always back drill all the stubs, or you should always just use blind vias. And the reality is that stubs don't really matter until you get into a certain frequency range. They also depend on the thickness of the stack-up. For now, let's take a look at the impedance and length tuning issues because those two are actually very closely related in any differential pair. This is not something that's unique to SFP interfaces. And we can look at the impedance inside of Altium Designer, and then we can look at what happens with meandering using a simulation in Simbeor. Now here inside of Altium, I have the layer stack manager open for the Ethernet switch project, and you can see here I'm on the impedance tab, and we can see here that we have a differential pair impedance profile defined with 100 ohm target impedance, and then here you can see what is going on with the outer layer dielectric. So if we go back into the PCB layout and we just go into 2D, remember that for this RX and TX pair, these were done entirely on the surface layers. So here you have the microstrip routing going into the SFP connector, and then here on the other side you have also microstrip routing going over to the network processor here in the center of the board. Now, there isn't a requirement to do everything as microstrips. You could do this as strip line routing, and you can even do high bandwidth channels as strip line routing. In fact, for a lot of high density processors where you have high ball count, for example on FPGAs that instantiate SerDes interfaces at 10G or 25G data rates, you're probably going to be doing a lot of that routing as strip lines. Now, one of the guidelines I like to provide for SFP routing is based on the trace width, and you can see here again in the layer stack manager, the trace width is 4.743 mil, or just over 0.1 millimeter. Now, if we go over here to the top layer at the SFP connector, you can see here that this trace width is much smaller than the width of the pads that the differential pair needs to route into. That's perfectly fine, and in general, I would say that the width of the trace should be less than the size of the pad that you're routing into, because we don't want to do neck down and change the impedance of that trace as it comes into that pad. So this upper limit on the trace width is going to put a constraint on the thickness of the dielectric that you can use in the stack-up. But there's one other lever that we have to tailor the trace width. Remember that that is the gap between the traces. If I were to change this gap to for example, 12.5 mils instead of 7.5 mils, when it recalculates the trace width that's required to hit this 100 ohm impedance, you can see that the trace width increases to 5.557 mil. So that's your first step with differential pair design. Pick a trace width that's going to be smaller than the width of those pads so you can route into the pads on the SFP connector without having to do neck down. That then is going to determine the spacing that you need between the traces in order to hit the impedance target of 100 ohms differential. Now typically for any high-speed design, I generally recommend that you use a thinner dielectric on the outer layer, something like 4 to 6 mil or 0.1 to 0.15 millimeters. That's going to force you to use a larger spacing value in between the traces in the differential pair, and that is important because it helps to reduce mode conversion and it reduces the impedance deviations once you start putting length tuning sections into the differential pair for length matching. Now to see why that happens, I've taken this board and I've actually loaded it into Simbeor, and we can do a quick simulation of the impedance along these traces where we have these meanders, and we can actually see how they impact the impedance of these differential pairs. So here you can see I have selected the differential pairs going into the SFP connector. I've also selected some of the differential pairs coming into the standard RJ45 connector block. So let's take a look at the differential impedance. So here you can see that the differential impedance is actually a little bit high, which is a little surprising, but you can see here what happens once we get into a length tuning section. So here in this region, you have the characteristic impedance. In this region, you can see what happens to the characteristic impedance as the length tuning section is applied. There's actually very little impact on the impedance in this design. So why did that happen? Well, that's because we used a 4 mil thick dielectric for the outer layer. And that smaller thickness for the dielectric and a larger spacing between the pairs helps ensure that you minimize these impedance deviations whenever you put a length tuning section here into a differential pair. We can see this result is pretty consistent everywhere else for all of these differential pairs coming into this RJ45 block. Now, what would happen if we used a thicker dielectric? Well, if we used a thicker dielectric, we would have to bring the traces inside the pair closer together in order to hit our target impedance, and we would have to use wider traces. Bringing those traces closer together will increase mode conversion once we apply the length tuning sections. So if you want to see some simulation results showing that, go check out our mode conversion video. The link is in the video description. Now, since we're talking about the PCB stack up, I of course need to mention the type of glass that is used in the materials in your PCB stack-up. Now, a lot of routing guides for Ethernet or PCIe or HDMI or USB or any of the other really high-speed differential interfaces will sometimes recommend the use of 15-degree zigzag routing or a full rotation of the Gerber outputs by 15 degrees in order to overcome the fiber weave effect. Now, the fiber weave effect is a real thing, and it creates problems with resonances or anti-resonances at around 50 gigahertz, which is something called periodic loading, where it creates extreme signal loss at specific frequencies. However, at much lower frequencies, the real problem is the potential to create skew along the length of a differential pair route, and that's one of the reasons that you will sometimes see that recommendation for zigzag routing. In fact, in some of Robert Ferenek's older videos, he actually shows examples of zigzag routing in some of the motherboards that he's designing on his YouTube channel. Now, the materials manufacturers in the PCB industry have understood this, and they have created something called spread glass. So what is the difference between standard glass and spread glass? Well, here I have a page pulled up on Bill Hargan's website. And Bill Hargan is the founder of Z0. And he's created a piece of software for calculating impedance based on stack-ups. Bill, if you're listening, I've been trying to get you on the podcast for years, so you've got an open invitation to come on the podcast and talk to me. But I have here a page pulled up on his website which really nicely illustrates the difference between standard glass and spread glass, or mechanically spread glass. So here, if we just zoom in, we can take a look at these two images and see what the difference is. So here in standard glass, we have all of these open regions in between these fiberglass bundles inside the PCB material. And with standard glass, when you press the material into a PCB stack-up, it more or less maintains all of these open regions in between the fiberglass bundles. So it's these open regions in between the fiberglass bundles that creates the fiber weave effect. effect. But with mechanically spread glass, what happens is those bundles will spread out and they will fill in all of the open space in this material once that material is pressed into the stack up. So once pressure is applied, all of those bundles will release and spread out as the resin flows during the stack up fabrication process. So it is the use of mechanically spread glass that has basically made that zigzag routing guideline more or less obsolete. You still get some skew from fiber weave effect when you have spread glass. It's just that the skew is much smaller than the case of standard glass. Standard glass could have skew in the range of 40 picoseconds per inch, while mechanically spread glass has much lower skew, anywhere from 1 picosecond to 7 picoseconds per inch. So that's about a factor 10 lower skew with mechanically spread glass. So the moral of the story here is, if you're worried about doing zigzag routing along the length of your SFP routes coming into an SFP connector, don't worry about it. Instead, just specify mechanically spread glass, and that's going to significantly reduce the trace-to-trace skew in that route. Now, spread glass doesn't mean that you shouldn't apply length tuning. You do need to apply some length tuning, but if you follow some of the guidelines I mentioned earlier, you will minimize the impedance deviations due to the application of length tuning, and you will minimize mode conversion. Now, the next important piece to talk about is via stubs, because if you look at a lot of high-speed design guidelines claimed to have been written by experts, they will always talk about removing stubs on every high-speed interface, no matter what the channel bandwidth requirement is. Now, stubs do create an impact in certain designs, but this idea that you need to remove every single stub, even from a device with, for example, 1G Ethernet, is kind of silly. It's actually very easy to calculate the frequency where you would expect to see a resonance due to the presence of a stub, and what you'll find is that even with a very long stub, those first order resonances are actually at pretty high frequency. Now, I have some articles on the Altium website that have looked at this from multiple perspectives. We have an article about a study of stubs on a PCIe connector, and this is a little study that I did with some guys at ANSYS. We can see the type of situation that we are looking at with these stubs. We have microstrip differential pair routing into a PCIe slot connector, and then you can see here that it is a through-hole connector. Now, the traces come in on the same layer as the connector, so this connector is basically leaving a long stub off of the bottom of those traces passing through the stack up. In this design, these stubs are basically 2 millimeters in length with a DK value of 3.6. Now, the conventional wisdom tells you that the presence of stubs will totally destroy the functionality of this interface. But really what you have to do is just look at where the resonance from these stubs occurs, and then use that to determine whether or not it will support the interface in question. Now, here we have some simulation results which were captured using ANSYS SI wave, and you can see here where the insertion loss starts to appear. The insertion loss starts to appear here right around 14 or 15 gigahertz. So what that means is that in this design on our Ethernet project, where we have these traces routing into this RJ45 connector block on the top layer, we also have stubs coming off of these differential pairs. And these stubs are about 1.57 millimeter in length because, of course, our stack up is 1.57 millimeters in thickness. So we would expect these stubs in this design to have similarly high resonances, somewhere in the 15 to 20 gigahertz range. So with all of these interfaces being 100 megabit per second Ethernet or gigabit per second Ethernet interfaces, we have no reason to worry at all about the presence of stubs on this connector. Now, what about our SFP lines? Well, you'll notice here that our SFP lines start over here off of the expansion PHY chip, and you can see here they start on the top layer. And then we route all the way through to the bottom layer. Then at the other end, by the SFP connector, we come up from the bottom layer right here, and then we come back up to the top layer. So because we're traversing the entire stack up, there are no stubs at all. The stub length is 0 on this interface. Now, that is the absolute easiest way to totally eliminate any consideration of whether or not stubs are going to matter in your design. You just eliminate them by routing across the entire stack up. Now, the typical case where stubs actually matter is shown in this article on the Altium blog. And this article is titled Your Complete Guide to Via Stub Analysis. Now, if we just scroll down here, you'll see that there is a simulation involving a single-ended via in a 10-layer, 2mm thick stack up. And you can see here the situation where a stub might arise. Here we're coming in routing on layer 1, and then the route ends on layer 3, but the stub continues all the way down to the bottom of the stack up, because of course this is a through-hole via. Now again, the conventional wisdom would tell you that any high-speed signal is going to be destroyed by the presence of this stub. But if you just scroll down a little bit, you'll see the frequency range that you can actually accommodate even with this structure that has a very long stub. You'll see that the first order resonance doesn't happen until about 22 gigahertz. Now, a first-order resonance of 22 gigahertz would equate to a third-order resonance of 66 gigahertz. And you can see right here that the actual resonance observed in the simulation data is at 65 gigahertz, which is really close to the theoretical value. They're only off by 1 gigahertz. Now we can see that this is totally consistent with the PCIe results from this other article, and we can see that the frequency ranges where we start to see this large insertion loss are similar. So for all practical purposes, that means for your 10G interface, you're really not going to have to worry about via stubs unless that board is incredibly thick. That 10G interface has a channel bandwidth requirement of 5 gigahertz, and you of course want to apply some margin above that, but you're not going to have a problem with stubs unless your board thickness gets to somewhere like 3 or 4 millimeters thick. That's a thick PCB. And in most practical applications where you're routing a 10G interface into an SFP connector, you really don't have to worry about those via stubs. But now let's suppose just for a moment that instead of working with a 10G interface, we were working with a 25G interface with NRZ modulation. Well, in a 25G interface with NRZ modulation, the channel bandwidth requirement is 12.5 gigahertz. And we can see that there is some insertion loss deviation once we start to get to that 12.5 gigahertz threshold right here where my mouse is on screen. And that's due to the presence of this stub. So in that case, we would want to either A, make the destination trace deeper in the stack up to reduce the length of the stub, or just put it on the bottom of the stack up, or B, we would want to back drill or just use a blind via. Now the formula for calculating these frequencies is given in this article. If you just scroll up, it is right here, and all of the other information that you need to understand this formula and how to use it. So if you want to take a look at this article, take a look at the link in the video description. Now the last piece to discuss here is the impedance of any differential vias that are placed on the route for your SFP connector. Now those differential vias do have a defined impedance, but that value tends to converge to the target trace value of, in this case, 100 ohms, up to about 3 to 5 gigahertz. Now I've shown a ton of simulation results in other videos on this channel, and I have a video linked in the video description that discusses that in more detail. So rather than redo all of that in this video, I'm going to point you to that video in the video description, and you can see what a typical via impedance spectrum looks like. Thanks everyone for watching this video, and thank you to everyone that's active on the Altium subreddit. Now we're going to continue to monitor the Altium subreddit, and as great questions come through, we're going to make sure that they end up in more of these videos. Make sure to hit the like button, hit the subscribe button, leave your comments and questions in the comments section, and last but not least, don't forget to call your fabricator, folks. We'll see you next time.